The sea came and went. Mountains formed and collapsed. Glaciers appeared and melted. The only continuity in our planet's history is change. When the late Ordovician glaciation came to an end, more than 50 million cubic kilometers of ice were transformed back into water. Sea level rose by 150 meters. The latest Ordovician, early Silurian post-glacial sea level rise is one of the most intense oistatic flooding events. Enormous amounts of coastal land suddenly were drowned. Within a few million years, the coastline was pushed inland many hundreds of kilometers. A large shelfal sea developed across North Africa and Arabia. Only Egypt stayed what it used to be, land, and formed a huge peninsula. The modern Barents Sea in the Arctic Ocean may be a small-scale analogue for what happened during the early Silurian in North Africa. Covered by ice sheets during the Pleistocene, the Holocene sea level rise transformed the Barents area into a large shelfal sea. Today the ice sheets have long gone, but the Arctic cold still has a firm grip on the area. The winters are tough. Surface waters are greatly cooled down and sink into the depth of the sea, as if to hide from the unfriendly forces of nature. Other, slightly less cold water masses rise to the surface and take over the vacant place in the winterly front line. The rising waters are bringing with them precious nutrients from the deep, food for tiny plants, the phytoplankton. As spring arrives, enormous amounts of Russian and Scandinavian meltwater enter the Barents Sea. The light, fresh water forms a stable layer on top of the seawater. The highlight of the year, because now, undisturbed by the winterly vertical circulation, the phytoplankton can finally concentrate on what they like most: food. Abundant light and great amounts of nutrients in the upper water layer generate a large phytoplankton bloom. Organic material that eventually sinks to the sea bottom in large quantities. As the summer approaches, the nutrients are finally all used up and the party is over, until it starts all over again in spring of the following year. The seasonal phytoplankton dance of the Barents Sea gives us a first idea that some cold water ecosystems are capable of producing large amounts of organic matter. The intense Silurian transgression in North Africa stopped all sands and coarse detritus at the river mouths. Only muds and some silts were able to exit onto the shelf, where they built up piles of hemipelagic mud. Rarely sand packages were mobilized by storms or gravitational instability at the coast and were transported onto the shelf as tempestite or turbidite mass flows. Despite the enormous rise in oistatic sea level, the northern Gondwanan shelf was initially not easy to conquer for the sea. It was surely not a flat platform or ramp, not at all. The glaciers had left behind a chaotic battlefield. A complex network of lows and highs dominated the shelf. Valleys and mini-basins carved out by ice and meltwater. Hills that had escaped erosion or that were newly formed by glacial fans or other glacial sediment dumps.
Clearly, a good understanding of the Ordovician glacial system can just be an advantage for the study of the basal Silurian shales.
What is the regional distribution pattern of the paleo valleys?
Where are they completely infilled with glacial sediment and where underfilled? where have they left some room for the Silurian transgressive muds.
During the initial transgression, only the low-lying areas, the paleodepressions, were flooded by the sea. Many of the highs were islands at that time, or they were covered by so little water that they were still in the turbulent wave zone, where only sandstones were laid down or non-deposition prevailed. The lows gradually filled up with mud, a very special mud, the fuel for hundreds of Saharan and Arabian oil fields, the Silurian lower hot shale, the basal part of the Tanisoft Formation. The black mud contains up to 18% organic matter of marine type 2 kerogen. It was formed during an anoxic event that occupied much of the early Chlandovery time at the very beginning of the Silurian.
During this time, the early days of the Silurian transgression, the paleo-highs acted as efficient flow barriers, preventing the establishment of large-scale water circulation. In addition, meltwater coming from the waning glaciers formed a light freshwater cap sitting on heavier saltwater. Lack of circulation and lack of vertical water movements blocked out any oxygen supplies to the basal water levels. Quickly, these waters turned into a dead zone. Organic matter arriving on the seafloor could no longer be oxidized and was preserved.
And there must have been a lot of organic matter. Some people say there was a giant upwelling zone in front of the northern Gondwanan shelf margin, pumping up great volumes of nutrients that formed the basis for rich marine life. A typical modern example of a coastal upwelling zone is the Mauritanian upwelling system in the Atlantic. Here, northeasterly trade winds push the coastal waters seawards, which are replaced by cool bottom waters rich in nitrate and phosphate. The nutrients feed large quantities of phytoplankton that forms the basis for zooplankton and fish. The Mauritanian upwelling system is active almost throughout the year and produces large amounts of organic matter. The early Silurian black organic muds were deposited across North Africa and Arabia, and probably as far away as South America and India. Not as a continuous layer, but restricted to the earliest Silurian paleo-depressions, a mosaic of hot shale patches surrounded by higher areas that the hot shales couldn't reach.
If we have a very deep low, so we have a very thick shale. So the hot shale has followed the pattern of the paleolows at that time, at the paleotopography.
On seismic sections from the Murzuk and Kufra basins, we clearly see the hot shale onlapping against the margins of the paleo-depressions. The hot shale is marked by strong seismic amplitudes as sound waves travel much slower through organic matter than through normal, organically lean shales. And there's also another very useful fingerprint that the hot shale leaves behind wherever it goes. The hot shale is markedly enriched in uranium and can therefore be easily detected on gamma-ray wireline logs. How does the uranium get into the hot shale? In all seawater, there are traces of uranium. In fully oxygenated waters, the uranium is dissolved as U6+. Under anoxic conditions, however, the U6+ is reduced to U4+, precipitates, and is incorporated into the sediment. Sediment that also accumulates and preserves large amounts of organic matter. And the data we have show that uranium, gamma-ray and total organic carbon concentrations are nicely interlinked in the Silurian hot shale of North Africa and Arabia. The higher the organic matter content, the more uranium is fixed in the sediment. So once this relationship is empirically established, it's easy to approximate the TOC using uranium or even total gamma-ray data from wireline logs. Using the characteristic gamma-ray hot shale kick at or near the base of the Silurian, the hot shale patches can be nicely mapped out. Based on analysis of all existing wells in the Murzuq Basin, we've identified a large, elongated hot shale basin that extends from the northeastern part of concession NC115 into NC174 and NC58, where our data suddenly end. The hot shale basin was surrounded by large-scale highs where the hot shale has not been deposited. When investigated in more detail, the hot shale distribution is even more complex and may change abruptly within a few hundred meters. Silurian Tanizuft outcrops occur in many areas around the Murzuq and Kufra basins. However, due to the shale's softness, in most cases only the middle to upper parts of the Tanizuft are exposed, protected from erosion by the overlying Akakus sandstones. Only in a few outcrops, erosion has not completed its job properly. It's here where the basal Tanizuft is exposed. And yet, for a long time, the only hot shale in the Murzuq and Kufra outcrops was cooked Tanizuft under the campfire. Till 2004, none of the numerous field parties visiting the Libyan desert ever discovered the Silurian hot shale at outcrop. A time of wild speculations. Were the Kufra and Murzuq margins possibly paleo-highs during the early Silurian and the hot shale absent? This would have had immediate source implications for blocks away from the basin center. Or was the hot shale hiding somewhere and just fooled the geologists? The hunt was on. And only a few years ago, it became clear that the hot shale was indeed hiding behind a weathering zone several meters or even a few tens of meters thick. Oxidation during desert weathering commonly penetrates deeply into the ground and destroys any organic matter in the shales. The black color is lost and reddish-greenish tones take over. As a consequence, the hot shale at outcrop looks identical to any ordinary organically lean shale. Technology had to be called in to help. Remembering the characteristic uranium enrichment of the hot shale in the subsurface, a portable gamma-ray spectrometer was dragged around the outcrops. The big question: did weathering also steal our uranium, or can we possibly use it to identify the hot shale radiometrically at outcrop? Uranium values in the first test section in the gut area were disappointing: 4.1 ppm, 5.2 ppm, 3.9 ppm, typical values of a normal shale. The second section, 19.2 ppm. A significant uranium enrichment was detected. Then 17.5, followed by 45.8 ppm. The hot shale gamma kick was found and the field team greatly excited. Uranium-enriched intervals were also found in various other sections, always at the base. Proof that the uranium hadn't moved. Finally, a tool was found to map the hot shale around the Murzuq and Kufra basins.
The main technique we used is called gamma ray spectrometer. So this technique, they measure all the radioactive material which are present on the exposure. If the result of this reading is more than 8 ppm, that means we have high concentrating of radioactive material, means the hot shale. And if less than 8 ppm, that's mean we have a normal shale or a cold shale. So that's why we can distinction by this technique between the source, between the hot shale and the cold shale.
A reliable tool, but heavily depending on the presence of basal Tanisuft outcrops. And the Gut hot shale also demonstrated that large parts of the western Morzuk margin were certainly not a paleo-high during the earliest Silurian. Otherwise, the hot shale would not be there. A glacial reservoir with a very complex sedimentary architecture. An extremely patchy Silurian source rock. The traditional layer cake stratigraphic model is dead. Today, the real challenges in Morzuk and Kufra exploration have become clear. But during the early 1990s, things still looked quite straightforward.
The initial exploration phase involved defining the petroleum systems. It seemed to be a very simple petroleum system, a Cambril Division sandstone overlain by a source rock, which was also a thick shale section, so that it was also the seal. The system seemed very simple, but in fact was more complicated than we originally anticipated. Those complexities were revolved around the complexity of the Cambril Division stratigraphy mainly. Understanding the Cambril Division fasces at the top of the Cambril Division section, and that's a reason for many failures in the Morzuk Basin. The sandstones are not in a good reservoir fasces. The other issue involved the sourcing and the charging of these prospects. It was very difficult to define the Silurian source kitchen, and the prospects with the highest risk, for example Elephant, should not have been sourced when we did our ortho contouring, and yet the ones with the lowest risks should have, and some of those were dry, or they had a small oil column on. I think what this says was we didn't fully understand the source kitchen story, the migration story, and thus didn't appreciate the risks. We were too confident in our understanding of the model. If we'd recognised more uncertainty, then possibly we'd have a more open mind.
Uncertainty and risk are essential parts of the hydrocarbon exploration game. We try to reduce uncertainty by working out models based on existing data that help us to predict the geology over large regional areas. When there's new data, we compare it to our model. After we've done this, we're either happy because the model worked well, or we simply refine or change the model. The traditional scientific approach. And yet, something seems to have gone wrong with this approach over many years in the Kufra Basin. In the 1980s and early 1990s, it was widely assumed that the Kufra Basin lacked any prospectivity because there was no Silurian source rock. The Kufra had been written off. And it had been written off on the basis of just 2 wells in a basin the size of Germany. The wells A1 and B1 NC43 had been drilled in 1978 and 1981 by Arjip Nami in the northern part of the Kufra Basin. The basal Silurian hot shale was indeed absent in these 2 localities, but how about the other 1 million potential localities in the basin? Even in a Silurian layer cake model, a layer extending over 400,000 square kilometers cannot be characterized by just 2 data points.
Then on such vast basins, 2 wells, they cannot tell the world about the source rock. It's not fair in Kufra Basin to downgrade the basin because of source rock based on only 2 wells in such vast, a huge size basin like Kufra.
And from the mid-1980s onwards, new drilling results became available from the Morzuk Basin that showed clearly that the Silurian hot shale had a patchy regional distribution. Still, the Kufra verdict wasn't changed. It took nearly until the new millennium for Kufra to get a second chance. A new depositional model showed that the presence of the basal hot shale is fully independent of the total Tanisoft thickness. A shallow borehole produced graptolite, proving the early Llandovery anoxic event at the eastern Kufra margin. Uranium-enriched shales were found in a basal Tanisoft outcrop section, and high-amplitude basal Tanisoft reflectors onlapped onto paleo highs on seismic charts. And there seems to be indications that the hot shale even produced hydrocarbons in the Kufra. A recent survey in the northern part of the basin appears to have documented local hydrocarbons microseepage. And in the southeastern portion of the Kufra basin in Sudan, Bedouins seem to use the oil from natural seeps to treat camel diseases.
The fact that there is reports of seepage in the southern parts of Kufra basin in Sudan makes the area exactly similar to Murzuk Basin, because Murzuk Basin, number one, was attracted by the seepage that was found in the southern area of the Gargaf, where these little towns of Gutta, Bergen, and Shati. And I think now the seepage do occur in the southern part of Kufra Basin in Sudan. So this makes the two basins are quite similar in many, many ways.
The Silurian world-class source rock has finally arrived also in the Kufra Basin. The question no longer is if there's a source rock, but how much and where. Southern Libya has never looked better than today. And things are happening fast. The first Murzuk field was brought on stream only in 1996. In addition, a string of discoveries in the past few years has finally proven the great petroleum potential of the Murzuk Basin.
Although it was among the latest basins where we have discovered oil among the sedimentary basins in Libya, but now I think the contribution of Murzuk Basin is more than the contribution of Gdamis. So I think for the time being we're producing something more than 350,000 barrels a day, and our target that's maybe will be production will be tripled maybe in the next 2 or 3 years.
Large parts of the Murzuk Basin are now licensed out and are being actively explored. To the pioneers of Libyan exploration, this activity may seem like déjà vu. Because even half a century ago, in the late 1950s, there was a time when oil companies flocked into the Murzuk Basin in great numbers in search of their bonanza. It all began in 1956, when a French consortium operating in eastern Algeria, near the Libyan border, discovered the large Etchella field in the Elysee Basin. Inspired by the discovery, several American and European companies came to Libya to explore the Gdamis and Murzuk basins. The first concessions in Murzuk were awarded in 1957, mainly in the northern and eastern parts of the basin. It didn't take long, and the first discovery was made in the Atshan area, located in a transitional position between the Murzuk and Gdamis basins. In 1958, Esso's well B21 tested here oil and gas. Although uncommercial, the Atshan discovery proved that the Silurian-sourced play works in the Murzuk Basin. The Atshan field consists of stacked oil and gas pools distributed over 5 different reservoir horizons between the Upper Ordovician and the Carboniferous. A leaking fault must have provided a nice conduit for the oil and gas to travel to the various reservoirs. Meanwhile, in the neighboring eastern Algerian Elysee Basin, more commercial discoveries had been made, all in Upper Silurian and Devonian reservoir horizons. Hoping to find similar fields, the companies operating in western Libya now specifically targeted this mid-Paleozoic reservoir play in Murzuk.
There was a general feeling that the deep Paleozoic was probably too difficult. There was certainly a feeling that reservoir quality was going to be an issue, that it had been deeply buried. and there was very little understanding about what the source rock system might be.
The attempts to make the Siluro-Devonian reservoir work in northern Morzuk failed at the time, maybe because the Tanisoft shale had effectively sealed most migration attempts of Silurian-sourced hydrocarbons into higher levels. New ideas were needed, for example, taking the reservoir risk and indeed search a bit deeper in the stratigraphic column.
Gulf also made a discovery this time, the A168, which discovered oil in Ordovician sandstone reservoirs sealed by basal Silurian shales, the Tanisoft formation. This turned out to be a key discovery, but it was pretty much ignored at the time.
They were busy years for the young petroleum industry in Libya. Companies came with great hopes and invested in their luck. By 1960, 70% of the land area of Libya was placed under license, including all of the Ghadames and northern Morzuk, but none of the Kufra Basin. There was still little data around. The creativity of the oil company geologists was needed. Some play concepts were simply copied from neighboring areas, others newly developed. Conventional ones and really crazy ones. It was clear the geologists needed to talk to each other. They needed a forum to exchange ideas and data.
The Petroleum Exploration Society, which is the pre-society before the Earth Science Society. It was established in 1958 and where an international group of geologists together with local geologists formed this society, and from that time on more information was accumulating every year.
And the main fellow who pushed that was Pierre Birollet. He also was the first one who initiated to publish a lexicon of stratigraphy. In 62 or 63, the first Sahara symposium took place in Tripoli. And there it was practically the first time when results of companies, of oil companies, became public. And it created an atmosphere of open exchange, of relatively open exchange of surface geology information. Not necessarily subsurface. Subsurface exchanges were in the normal terms. You offered a certain well and you got another well in exchange, but surface geology was relatively open exchange. I was the one who got the award for the best paper, which was very interesting because at that time I spoke much worse English than now, and as you can hear, my English is not the best. But it was mainly due to the fact that I was the one who first understood, or at least who first published and talked about it, that there was a definite change in structural behavior, structural setup towards the end of Silurian. In other words, what we in Europe would be Caledonian geology. And the place to see that, and the place where I understood it, is northern Dorogoza at the eastern edge of Morzuk Basin. And I must say the position I had within DEA was an excellent position because I had a head geologist or exploration manager in Hamburg, which not only tolerated scientific work or this type of interpretation and publication, who also encouraged it. He was a scientist and was happy that his men worked scientifically, and he was happy to go with us to the desert. We took him several times to southern Libya, even to the Besti and to northern Niger. And I remember the first trip he was called back to Hamburg at the third day. That had one consequence. On the next trip, we turned off the radio. We told him it was broken. And so we made our 2 weeks in the desert without having the order for him to come back.
It was characteristic during this phase that companies didn't rule out any region without having actively explored it, also in the Murzuq.
There was further drilling to the south, and indeed a number of wells were drilled in the Niger extension of the basin, in the extreme southern part of the basin, but all with generally lack of success.
Despite a few uncommercial discoveries, companies soon lost interest in the Murzuq. And this did not even have much to do with the Murzuq itself, but with some interesting geophysical results from northern Libya.
And meanwhile, oil companies had undergone quite a bit of gravity and magnetometric surveys, and found out that the area between Achedabiya and Benghazi, which we call now the Sirte Basin, is an area with very distinct subdivision into graben and horst structures with deep graben floors, and so consequence was to concentrate more in that area, and within one of the first wells a large oil field was found. And this was the end of at least intensive exploration in other areas.
The Bahi field in the Sirte Basin was the first commercial discovery of Libya, found by Oasis in April 1958 by their well A132. In that same year, 6 other discoveries were made in the Sirte, nearly half of them were declared commercial. And all this during a time when in western Libya there were still no commercial finds in sight. The Murzuq had lost the race. Exploration in the following 30 years now concentrated mainly on the Sirte Basin.
I believe the reason that Murzuq Basin was not considered to be very attractive in the early days has, of course, several reasons. One of it is big oil fields have been found in Sirte Basin. The first wells which found oil in Murzuq Basin or bordering areas did not find much. The test results were in the order of a few hundred barrels maximum, while in the Sirte Basin it was several thousand in average. So this is one reason. The second reason is the distance to an harbor or to the Mediterranean is drastically larger, bigger than from Sirte Basin. And the third reason is the Homra or Ghadames Basin was under exploration relatively early, because this is logical. It was the area east of the successful oil exploration of Algeria and southern Tunisia. So Echelay, for example, is at the Libyan border. And there was no reason why there should not be oil in the Ghadames Basin. Ghadames Basin underwent a very intensive seismic interpretation. It was full of seismic lines. It was difficult to find your way across Homra Basin. I went several times from Ghadames to Awenat, and I lost my way several times because of that. But whatever oil was found on Ghadames Basin was little oil, was no big field, not at all. And I think even up to date is no big field in Ghadames Basin. And it is a similar basin as the Murzuq Basin. This is Paleozoic. It is similar deep, but closer to the sea, not successful. So why should people go to the Murzuq Basin? I think that's the whole reason. We tried very hard to get our company, which was DEA at that time, to drill Jebel Ati, which is even further south. I mean, it's southern part of Murzuq Basin. A very large, 80 kilometers long and 10, 15 kilometers wide anticline. But this was impossible to convince any management, and I think other companies had the same problem. We were not the only geologists which were interested in the Murzuq Basin, but we had no success to convince management.
During the 70s, exploration was pretty dormant until Brass Petro moved in the late 70s and followed through with a very aggressive exploration program, drilling wildcats in many parts of the basin. Again, that was unsuccessful.
And also Occidental tried their luck in Morzuk at that time, but these efforts were not rewarded either. Until this point, the Kufra Basin had been hardly looked at. Not a single well had been drilled, but this was to change. In the mid-1970s, Ajip Nami carried out a full-scale exploration program in Kufra. An enormous amount of outcrop, aeromagnetic and 2,200 kilometers of seismic data were collected. But 2 dry holes brought this campaign to an end as well. In the 1970s and early 1980s, geological concepts and technology were not yet fully developed to make explorers believe in the prospectivity of southern Libya. But most of all, they lacked one thing: luck.
At that time, before 1980s, it was considered as a frontier area, and that the exploration costs will be very high. So the people now, they were not encouraged to work there and to explore that area. Plus, even because of the reservoir pressure at that time, the wells never been flowed to the surface. So that's another negative point at that time. But nowadays, and plus the cost of the barrels of oil at that time does not encourage people to explore that area.
Undeterred by the past failures, Eastern European companies stepped onto the Morzuk scene in the 1980s. The Bulgarian Bokul and Romanian Rompetrol explored large areas of the basin and understood quickly that it was in fact the Ordovician sands that were the most rewarding target.
We have 3 companies working on that time in this area. It was Rompetrol, Bokul and Braspetrol. These companies, they have the very, I can say, huge blocks. The smallest one was for Rompetrol with 25,000 square kilometers. Myself, I joined Rompetrol in exploration stage in 1984 as a trainee geologist in exploration department, and from there we started.
Between 1982 and 1985, Rompetrol discovered various large fields in their concession 115 and laid the foundation for the oil boom in the region today.
Rompetrol, I think, had reserves of 500 million barrels in the A field. Repsol bought the Rompetrol interest and found that there was indeed a lot more oil than they originally thought in those fields. And Repsol went about drilling new prospects, shooting new seismic 3D. The quality of the seismic data of NC115 is excellent because it's on a flat sand plane.
While lack of funds prevented the Romanians from developing their own discoveries, they were indeed the first company in Morzuk to earn money from their activities. After the transfer of the Saharan field to Repsol in 1994, the reserves were re-estimated to be more than 1 billion barrels in place. Development was completed in 1999, and today the field produces about 160,000 barrels per day.
So when Repsol joined the NC115, so they are found 3 main or 3 major oil fields, which is called A field, B field and H field. But now we discover and we develop the whole NC115. So at the moment we have 4 main fields, I mean A, B, H, including M field, and we have also a small structure which is called N structure, O structure, and we have another small structure called J, F and C structure.
Some of them is under development, other ones is planned to develop very soon, and other ones is postponed. Depend on the size of the field and the relation with the surface facilities. But we make our plans to reach to our production quota. Okay, and we are now on a good production level. I can see that we have a very good rate of success. Means that a lot of new discoveries achieved recently, which is giving us more interest points for the basin.
I'm surprised once Petroleum made the discoveries in the NC 115 block that more companies didn't look at the basin. And looking back, there was a prolific source rock there, world-class source rock. There was a good reservoir system. It's surprising that it wasn't recognised earlier.
Following the Saharan giant oil field discovery in 1984, it took another 13 years for the oil industry to land the next commercial discovery. In 1997, LASMO eventually found the giant Elephant Field. Since then, various other fields have been discovered in the Morzuk Basin by Repsol, Total and partners.
During this period, the central and southern part of the basin was largely ignored. There was very little drilling there. But ultimately, around about 2000 or so, people started to think about the area and gradually moved down. Repsol drilled a well in the central part of the basin and helped drill several wells in the Niger extension. Again, these were unsuccessful. In 2004 and 2005, Libya had the first of the EPSA-4 rounds, which have really triggered off a new round of exploration in this area. And now we wait to see the results.
Looking back at 50 years of trial and error exploration in Morzuk, activity can be split up into various phases. The presence of a working petroleum system was proven very early on. In the following 30 years, the basin was largely forgotten as interest had shifted into the Sirte Basin. From a historical perspective, was it probably a mistake to have overlooked the great potential of the Morzuk for so long?
I'm not sure I would consider it to be a mistake to have overlooked that evidence, if you like. The evidence was very clear. I think it was much more a question of priorities. There were other places that we wanted to explore first that were nearer to facilities, that were nearer to populations of centres of population, nearer to the coast, so we had a better export route. So I think it was simply a question of priorities. I think we recognised that there was good evidence that there were other petroleum systems around, but we simply had other priorities at that time.